Good morning, everybody. It's a great pleasure to be here. So we're going to talk a little bit about the technology that was essentially originated exactly from the point that Tudor just made, focus on improving workflow. And all these technologies at this point, they are converging, right? So they all work with workflow, CT perfusion, infarct detection, so on and so forth. So here are the conflicts. This is a non-CME presentation and part of the Physician Advisory Board. So the stroke care, the standard form, it's a linear algorithm, right? So the patients come to the emergency room. They are triaged by the stroke team. You have radiologists, you have CT scan, ED physician, and these things, they happen in series. The idea of the VizAI software was to create a parallel universe. And many of us have this misconception that AI is here to replace the human work. At least at this point in time, the goal of AI is actually to optimize what you do. So when you look at these numbers, how AI performs in general, you shouldn't necessarily compare it with human performance, but you should compare human performance alone versus AI optimized human performance. And the idea here is to create this parallel universe where you still have the regular workflow, but here you have the AI help that can potentially expedite the diagnosis and then cut down times and lead to better outcomes. So what is Viz? So Viz is a complex solution that it's AI-based. There are 4 systems that are currently approved by the FDA. There is a system for LVO detection. There is a CT perfusion automated analysis system. There is a DICOM viewer and a HIPAA-compliant communicating system. And all this converges to full automation and communication, which happens in parallel to the whole team. So starting with the Viz LVO, again, the idea here is to create this parallel universe to expedite the times to treatment. But I was always curious to understand how does this actually happen, right? Here is what you typically show. We have an input layer, you have the deep neural network, and you have an output layer. But how does this deep neural network actually works? What happens in the black box? So there are several different steps that the neural network will process for us. So the first thing that it does, it looks for contrast in the CT scan. After that, it excludes the presence of metal because that would create artifact. There is then segmentation processes where you compare left with right, and the algorithm then traces a central line across the vessel and extends that, and then it can compare the different lengths from one side and the other. And now these things have preset thresholds that will trigger an alarm. Finally, the system looks at these central lines and see if there is a drop in the Hounsfield unit across this line. So if you have contrast, lack of contrast, or less contrast, and then more contrast, it also triggers a response. And here is how I would summarize this. So you have the soft matter of the CT scan is extracted. The system then looks for Hounsfield units that are consistent with the presence of the iodine contrast agent. If that doesn't happen, there is no further processing. It's not a CTA. If this happens, the system then is going to look for Hounsfield units greater than 3,000, which represents metal. If there is metal, it can trigger a false positive case because of the artifacts presence, and then it's not going to process that. Otherwise, the system crops the circle of Willis, processes it in a 3D manner, and then it segments the whole ICA and MCA all the way to the insula to identify occlusions in the ICA M1 and M2, compares right with left, segments, extend both sides, compares the lengths, and there are, as I said, predefined thresholds that at these points will identify and trigger the notification for LVO. If none of this happens, it looks at the central line for Hounsfield units drop, and then it will trigger the message if that happens. And that's how the systems can actually identify partial occlusions, intracranial atherosclerotic disease, even moya-moya cases. We typically see those cases. So this is kind of the workflow. It finds the patient based on the metadata. It will then get the head mask extraction. It will do the image analysis to detect the exclusion criteria based on the iodine contrast and metal. Then it does a registration to then fully align the scan and create the 3D circle of Willis. Then you can see here the segmentation working, and then the right to left comparison, which will trigger an LVO in this case. Then it extends the central line. You can see the central line growing here. And then you can see again, it's going to look at the lengths, and there are the thresholds that will trigger the response here again. And it will measure that central line, as I explained. We will inspect then for all these potential triggers, and will generate an automated notification to the user and the whole team. Here are a few cases. This is an easy one where you can clearly see an ICA, and the system finds the ICA for you, ICA occlusion. Here is a proximal M2 occlusion where the system finds it as well. Here is a case where you just have a partially occlusion or intracranial stenosis, where the system can easily find that as well. So what is the data that you have in the LVO detection software? So in our center, you have reviewed approximately 590 cases. We did this with an enriched population of LVOs, because that's what we're expecting to detect. So 70% of the patients approximately had an LVO. And use a version of the software that it's not the last one, but the previous one to that. And you compare that with the experienced stroke neurologist and radiologist reports, and the goal was to identify intracranial ICA occlusions from the supraclinoid segment and up outside the bone canal, and M1 occlusions. This was the primary analysis, and more recently the system was trained to find M2 occlusions as well. So what you can see here is, in terms of our primary goal, the accuracy, it's essentially 90% with sensitivity and specificity in that range of 90%. Once you add M2, the accuracy drops to 83%. The system is still training and learning. It gets better over time in terms of finding the M2s. It does a lot better with the more proximal M2s than with those Gs to M2s along the ends of the insula. The processing time is extremely rapid. It's less than 3 minutes. I think another point that it's interesting to talk about is the early data that you have on CT perfusion. It's good to compare different technologies. The predecessor actually for CT perfusion was the Aulea system, but that really never panned out, which is a lot more established, as Tudor said, based on all the clinical trials that you have, including Diffuse 3 and DOL, is rapid. So what you did here is you compare the volumes that it would trigger a treatment case, right, in terms of the CTP parameters with rapid and VizAI. And as you can see, there is essentially extremely good alignment, to the point that in 95% of the cases, the two softwares would say you should treat this patient by either criteria. And you can see here the same thing when you use the DOM criteria for core analysis across the different sub-items of DOM, in terms of less than 21, 90%, and essentially 98% for less than 31 and less than 51. One of the things that was interesting is, because this is an AI system, it has an optimized motion correction software. So when you look at the CT imaging that was impacted by motion artifact, that motion correct software actually could improve the images, as you can see here. It had a lot less errors in terms of imaging processing. You can see some examples here where you can see the two different softwares. You see here a lot of the Tmax greater than 6 lesion. It's actually crossing to the other side, and that does not happen with the Viz CTP software due to motion correction. Okay? Another case here where you see posterior fossa and contralateral Tmax errors, and again, with the motion correction of Viz, you don't see that. There are cases that are beyond help. Obviously, when you have something like this, you can get still some improvements, but we still have issues when you have a lot of movement artifact. And here is another case again where you see posterior fossa and contralateral contamination in the Tmax greater than 6 with rapid, but with AI automated motion correction that disappears. Some more cases, again, just to show essentially the same phenomenon. Here is no AI technology for motion correction, AI technology for motion correction. Again, more of it here where you see the classic Tmax contamination throughout both sides, and this does not happen with AI motion correction technology. This is research that you've been doing at our center. It's essentially for automated identification of intracranial hemorrhage and automated volume measurement of intracranial hemorrhage. As you can see here, this is something that it's getting more and more attention because all the clinical trials for early evacuation of hematomas or early intervention with prothrombotic treatment or fibrinolysis. So what you have done here is we have analyzed 284 cases, out of which you had 132 cases of intracranial cerebral hemorrhage, and then you compare the identification and the automated software performance with the experienced stroke neurologist and the automated, semi-automated measurements done on Osiris. As you can see here, the accuracy of the system was 96% with a sensitivity of 95% and a specificity of 99%. Again, this is not yet approved. The 510K is still pending, but I wanted to show our initial research on this topic. So to conclude, this is a very comprehensive solution. This is not about dealing with CT perfusion only. This is much more focused on improving the whole workflow of the patient, computing imaging processing, imaging viewer, and communication systems through a HIPAA-compliant system to get you this net result of a marked improved, expedited workflow, which should lead to better outcomes. Thanks a lot for your attention.